Pre-calculus, chapter 6, lesson 1, and I want to do one example where we take some of this vector arithmetic that we've been working with and we apply it to a problem. In this problem, we have an airplane that's flying at a heading of 170 degrees and its ground speed is 460 miles an hour. And then we have a wind that's blowing at a heading of 200 degrees and its speed is 80 miles an hour. What would be the components of the resultant vector, and then what would be the actual speed and direction of the airplane? Now, there's two parts to this. The components of the resultant, when I see this resultant, I get a resultant vector by adding two together. So what I'm going to need to do is to create a vector for this airplane, create a vector or find the components of a vector for the wind, and then simply add those together by adding the component. So basically that does the adding of vectors that we talked about. The second part of the question asks me to determine the actual speed and the direction of the airplane, knowing that I have the force and magnitude of the plane speed and the wind acting together. Well, that simply means what I'm going to need to do is, once I have the resultant vector, I can figure out the actual speed. That's going to be the magnitude. So once I have the resultant vector, I'll simply do the magnitude calculation to figure out the speed. The direction's a little bit more difficult, but again, it involves something that we already know. And that is that if we know the component is equal to the magnitude times the cosine of the angle, or the magnitude of the B component is, the B component is the magnitude times the sine of the angle. So in order to determine the direction, I'm going to need to determine this angle. Well, once I know the resultant vector, I'll have the A, and I'll be able to calculate the magnitude, so I can substitute those two values into this expression and then solve for the angle. There is one other way you can do this, and I'll talk about that when we get there, but that's what we need to do. So let's go ahead and begin doing this. So the first thing I need are the components of the airplane. Well, if I think about this, again, the direction angle, because it's navigation, is measured from due north. So if this is my imaginary line at due north, 170 degrees would be something like this, 170 degrees. And then the length of this would be 460 because that's its magnitude. Now what I need are these components right here. What are the A and the B of this vector? Well, the A component, you remember, is equal to the magnitude, which I know is 460, times the cosine of the angle. Well, in order to figure out the A, I need to know what this angle is. You remember that the angle of the vector is measured from the positive x-axis. So if this is 170 degrees, the difference between this north and this, which would be east, is 90 degrees. So if I take 70 or 170 and subtract 90, then the measure of the angle from here to here is 80. And because it's going down and we're using trigonometry, this would be a negative 80-degree angle. So in order to figure out the A component for the airplane, I simply take the magnitude of the vector, which is 460, times the cosine of this negative 80-degree angle, and that will give me the A component. The B component I would then figure out by doing 460 times the sine of this same angle. So by doing those calculations, I'll be able to determine the components of this airplane vector. I'll then need to repeat that process to figure out the components of the wind vector. And again, it's going to be the same thing. Very quickly, I'll sketch it out here. If this is north, 200 degrees would be about over here, because 180 is half a circle, and then this would be 20 more. And the length of that would be 80. And again, if I want to use the vector, I need to use the cosine angle, or the cosine of the angle. So I'm going to need to figure out what this angle is. Well, it's 200 degrees, so if I subtract 90, that's going to give me the difference from here to here. So that's going to be, again, a negative angle of 110. So I need to figure out the components or the coordinates of this vector. Again, the A component is the magnitude, which is 80, times the cosine of the angle, negative 110. And the b component is 80 times the sine of this component, which is also 110, or the angle, which is still 110. So by doing that, I'll be able to calculate both the components of both vectors. And I need those because I need the resultant. So all I'll need to do is to add those two together once I determine what they are. So having done those calculations, I come up with the components of the airplane as 79.8782 and then negative 453.0116. Now, I went all the way out to 10 thousandths place here because I'm going to be using these numbers in other calculations. So in order to make sure I get a more accurate answer at the end, you should go out at least 4 decimal places in these intermediate calculations. And I drew a little picture over here of where the vector is to kind of double check and see if my components make sense. You remember my airplane was going at 170 degrees, which would be about this direction. So if I took this coordinate, 79, which is positive, and down negative 453, those components make sense as to where this point might be. Positive 79, negative 453. And then the components of this vector also make sense. A negative x value and a negative y value makes sense as to why those are both negative, so that kind of makes sense. Now, in order to figure out the result of both of these vectors, the plane speed along with the airplane, I simply add these two vectors together. And you remember, vector addition is pretty easy. We simply add the a components, and then we add the b components. So to add those components together, I get my resulting factor of 552, and again 5.5166, and then negative 528.187. So this is the answer to A, taking these two components and simply adding them together. Now, to determine B, I need to find the actual speed, which is simply the magnitude of this vector. So the magnitude of the vector, you remember, is simply the square root of the A component, 52.5166 squared, plus the b component, negative 528.187 squared. And so we'll make that calculation, and that will give us the speed of the airplane. So that gives us a resulting speed of 530.79 miles per hour. So the magnitude of this vector is 530.79 miles per hour. To determine the direction angle, there's a couple of different ways we could go about this. We know from the equation that the A component is equal to the magnitude times the cosine of the angle. We could determine the measure of the angle by doing the inverse cosine of the A component divided by the magnitude, and that's just algebraically manipulating this. Divide by the magnitude and then use the inverse function. So we could use the inverse function of the component, which is 52.5166, divided by the magnitude of 530.79. The only thing we'd have to be careful about there when doing this is remember that the cosine function on our calculator is going to give me the angle measure up in here because that's the range of the inverse cosine. The problem with that is if we took a look at these components, the actual angle of the direction of the airplane is this angle right here. And so the angle that it gives me would be somewhere up here, and I would have to make the necessary correction to make sure it's here. The other way, or another way to do this would be to use the sine. Because I know that the angle is down here, and I know that the range of the sine function, inverse sine, is over here, that would give me the angle here, and then I need to make the adjustment that the navigation angle, remember, is measured from due north. There's one other way to do this, and I think this is probably the easier of the three ways, and that is to use just a little bit of trigonometry. Meaning, if we take the components, which we now know, if we go right 52 point, why do I keep writing 55? If we just plot this point, so this is going to be 52.5166 going this way, and then we go down 528 negative 528.187. Okay, and we draw this, and sorry for my drawing, I'm going to have to make a little adjustment. Here we go. This is a right triangle, and I want to know what this angle is. Well, this is opposite over adjacent, so I could use the inverse tangent. In other words, the tangent of the angle then is equal to the opposite side, a negative 528.187 over 52.5166. And then solving for tangent, we again would use the inverse function here of negative 528.187 and then 52.5166. That way I know I'm getting this angle here and I don't have to worry about the inverse function problems with cosine or with sine if the angle is in another quadrant. So by doing this, that's going to give me this angle, but we have to remember that the direction angle needs to be measured from due north. So I'm going to need to add this 90 degrees from the direction angle to my angle here in order to get the direction from due north. And you're going to have to do that no matter where your angle is. If the airplane ends up, being over here in quadrant 3, you're going to have to determine this angle, but then you're going to have to add these other angles in to get it back to direction angle from due north. So just keep that in mind as you do these problems. So when we calculate this angle, then we get an angle of a negative 84.32. So this angle here is a negative 84 from here. All right, but we're interested in just the direction angle, so we can ignore the negative sign. That's just because it's measured from the x-axis and it's a trigonometric angle, so because we went clockwise it's negative. And then we want to add to that an additional 90 so that we have the angle measured from due north. So if we add 90 to that, whoops, we want to actually, because I did that. So if we add that 90 to that, we get a direction angle of 174.32 degrees. So the answer to B is the plane will be going 530.79 miles an hour, taking into account the speed of the airplane and the speed of the wind acting upon the airplane. And the direction angle will be 174 degrees, again, because of the effect of the wind on the plane. And so that's how we would apply vector arithmetic in a problem where we can have the directors or the components of the vectors and use the arithmetic to discover the speed and direction after two forces are acting on an object. So just remember as you tackle these word problems or applicational problems, the arithmetic is the same for all of these problems. We spent a lot of time with the arithmetic learning how to add vectors, learning how to calculate the magnitude, which is the length of the arrow, and we talked about the direction angle. All of that is really nothing really complicated. You just have to remember what those terms mean and then what you need to calculate.